You know, I forgot to bring my printed out. Whatever. Okay, I'll survive. Okay, so I want to start with so I asked you to do exercise 1, exercise 3, and exercise 5, right? Where did the exercise 5 go? So exercise 1 and exercise 5 can technically be done entirely from the output presented in the textbook, okay? But exercise 3 requires you to fit models and transform data yourself in R. So I was going to start with that. Well, you know, once I finish that and address any questions that you might have about exercise 3, then we can talk about exercise 1 and exercise 5, where you use their output. And if you wanted to, you could fit your own models as well to try to improve and things like that. Okay, but let's take a look at exercise 3, okay? So exercise 3 says the price of advertising is different from one consumer magazine to another. Publishers of consumer magazines argue that magazines that reach more readers create more value for the advertiser, and thus circulation is an important factor that affects revenue from advertising. In this exercise, we're going to investigate the effect of circulation on gross advertising revenue. And the data are for the top 70 US magazines ranked in terms of total gross advertising revenue in 2006. And we're going to develop regression models to predict advertising revenue per advertising page in thousands of dollars from circulation, which is recorded in millions. And the data were available from here, and let's do this. Okay, so part A says, develop a simple linear model based on least squares that predicts advertising revenue per page from circulation. And it says, feel free to transform either the predictor or response variables and ensure that you provide justification for your choice of model, okay? And then it says, find a 95% prediction interval and describe weaknesses in your model. So let's start off here. Okay, so I'm going to begin first by loading the data. So this is in your, let me just clear out my environment over here, and we'll clear the screen. Okay, so this block of code comes directly from your R Markdown file. So here I'm just loading the data into our Markdown, and we see we have two columns that are not relevant to us. That they provide information such as People Magazine and Better Homes and Gardens, Time. These are the magazine, and we can see here if we click View here, we can see okay, People Magazine has a circulation of 3.75 million. Better Homes and Gardens has double that at around 7.639 million. Time has a circulation of 4 million. Parade has a circulation of 32.7 million, So these are, we have these huge discrepancies, right? So some are way bigger, okay? And then, we go down here and we see PC Magazine, has 723,000 subscribers. Esquire has this. Town and Country and Modern Bride don't have many. Okay, and so we want to just start by maybe just exploring the data, right? So I'm going to do Ggplot, and this is what. If I just plot circulation versus ad revenue, we see this, okay? So we see a lot of points concentrated down here, and then we've got just a few data points out here, okay? So there's not a whole lot, but can we accommodate these in our model, okay? So we're going to start off by doing, we're gonna just fit a linear model and see how this goes, okay? So the first command I'm gonna write is I'm going to write model is a linear model between ad revenue and circulation where the data comes from ad revenue, the object ad revenue. Okay, so this is my model. We can come down here and ask, what is this, what does the summary of our model even look like? Okay, and it says stuff like this, and we're like, huh, okay. But then, if we plot it, so I'm just using Ggplot with geometric geom point and adding a linear model smoothing curve. Okay, this is our straight line fit. Okay, and if we look at this, it doesn't look like it's very good, right? Sure, it accommodates these ones out here, but if we look down here, this looks very bad. Okay, this does not look like a very good fit. And we can do our diagnostic plots. Okay, so you can, we can just do plot model. Okay, and this will just do our kind of the base series of diagnostic plots. Okay, and when you do plot model, it'll say hit return to see the next plot. Okay, and so this is residuals versus fitted. Okay, and as far as scatter goes, it seems like we get this kind of funny offshoot here, and and all the points are concentrated down here, and there's just not a whole lot coming out here. Okay. We can go to the next. This is the normal QQ. Okay, and we see some serious concerns, reason for concerns, right? Our standardized residual, we got -4, and then also up here things that are pretty high, but we're getting standardized residuals of -4, which seems worrisome to me. Okay. Here's our scale location plot. All right, and so down here, we're definitely seeing something here. Out here, because these are so far out there, you're not going to have we just don't have a ton of information out here, and we're trying to fit a model kind of based on that. All right, and this one, we have some, like the Cook's distance of some of our points are just very, very extreme. Okay, and so we're missing the data point, but there's a Cook's distance. One of these has just a very high Cook's distance. So you can just run Fortify model, which is comes with a Ggplot 2, and when you do that, one of these things is Cook's distance. Okay, and where is the one I'm looking for? So I think this one has a Cook's distance of about 4, right? So e to the 01 is to the first power, so we see this one has a very high Cook's distance. Okay, so anyway, we'll see what we can do. Okay, so this means we should probably transform our data. So we're going to create histograms. We could create QQ plots, but I'm going to create a histogram for our x variable. Okay, we just want to see what is our x variable. So circulation is very heavily right skewed. Okay, and we look at we're going to create a histogram for ad revenue. Okay, and ad revenue is also very heavily right skewed. Okay, and I don't have the code here, but we can also just do QQ norm of ad revenue $ circulation and QQ norm ad revenue $ ad revenue. Okay, so let's take a look here. Okay, and we see, okay, very clearly not normal. This thing also very clearly not normal. So this seems to indicate, both are very skewed. So we're gonna try a power transformation on both variables. Okay. All right. So the commands that we use for the power transformation can be found in library CAR. CAR is Companion for Applied Regression. It's a textbook, but it's a well-respected textbook, and you know, you might be able to find it. Companion to Applied Regression. I mean, look, I think it's called the R Companion to Applied Regression. Yeah, this is the textbook. It's a textbook, so of course it's overpriced or just it's expensive, but they have it at Google Books. And one of these, is it the 2011? I think the 2011. You can read quite a few of the pages at Google Books. Okay, so there's a good section on transforming variables from Google Books, or you can check it out at the library also. Okay, so anyway, we're going to load library car, library dplyr. Okay, and the command here is we're going to apply a power transformation. Okay, so let me just break out this code here. Okay, I'm applying the command power transformation to add revenue, just the third and fourth columns. Because if I try to apply, so if your data frame only has 2 columns and they're both numeric, you can just do power transformation the data frame. Okay, but here, because the values we want to transform are in the third and fourth column, I'm going to do power transform add revenue third and fourth columns, which correspond to ad revenue and circulation, right? So if we recall the structure, ad revenue is the third, so our Y is in the third column and circulation is in the fourth column. Okay, so I can do power transform here, and here it just estimates the power transforms that we should use. Okay, so it says, I think the power transform you should apply to ad revenue is negative 0.587, and I think the power transform you should apply to circulation is negative 0.24. Okay, you can get some more information if you do a summary of the power transformation. So if I do power transformation, and if I say summary of my power transformation, okay, it'll tell you what transformations it thinks you should do, and it also gives you these funny p-values, which I'll talk about here. Okay, so and so basically that's what I'm doing in this command here. I'm just saying do the power transformation, but actually store the results in an object called power, and then give me the summary of that. Okay, so that's all I'm doing in this command. So I'm saying do this. Okay, and so we get this this funny looking thing here. Okay, and so what this does is it does likelihood ratio test, and it says what if we did a power transformation and we applied a power transform of 0 to both the x and the y variables. Okay, so 0 to the first one, which is our y, and 0 to our x. Okay, is that a good idea? Well, the p-value comes out to be really tiny, which in our case we don't want, which in our case says this is not the appropriate power transformation to apply. Okay, if 1, 1 means leave the data as is, leave y and x untouched, and this also says this is a terrible idea. Okay, the p-value comes out small, and it kind of defaults to trying to use nice numbers here. So it says the first one we got negative 0.5, so the closest thing, negative 0.587, the closest number here is going to be negative 0.5. Let's see if that works. And then here, negative 0.24. It kind of prefers half and a third over a quarter. So we can apply a transformation of 1/3, and it says what's the p-value associated with that? It comes out 0.12, which is actually would be insignificant, which means maybe this is the appropriate transform here. So it's kind of the reverse of what you're used to with p-values. In this case, a large p-value would indicate that this might be the right transform to use. Okay, so here you have some options as to what to do. You can use the estimated power transform that it gives you, I have opted, personally, I have opted to use negative 0.5 and negative 0.25. So raising it, basically taking the square root, essentially, or the negatives, well, raise, you know, inversing it and putting the square root on the bottom, okay, right? Raising it to the negative half power. And here I'm going to raise it to the negative quarter power. The textbook for CAR says probably 1/2 and 1/3 are good enough, but in our case, because it's coming out down here, I'm going to try out a quarter, negative quarter power. But people might differ on that opinion. So I can apply this. So remember, what is the formula for a power transform? Is well, this applies the so here's the standard power transform. You do y to the lambda minus 1 over lambda, okay? And so if we wanted to apply the power transform to our data, we would take add revenue, raise it to the lambda, subtract 1, and then divide by lambda, right? So dividing by negative 0.5 is the same as multiplying by negative 2. So I'm applying the power transform right there to y, and this I'm going to get transformed y here. I do the same thing for the power transform of x. I take circulation, raise it to lambda, subtract 1 from that result, and then divide by lambda, or in this case, multiply by negative 4. Okay, and so I can do, I can apply the transform, and I can say, let's take a look. Let's just do the head of transform, okay? And we can see transformed y and transformed x looks like this. Okay, so you take 233, you raise it, you apply this, and this is the number you get, okay? There's a command in CAR called BC power, basically Box-Cox power transform, and you say, what do I want you to do? Take the columns and add revenue, take the third and fourth columns and add revenue, and to the third one apply, or to the first column you see, which is the third one, apply a negative 0.5 power transform, and to the other one apply a negative 0.25 power transform. So if I do that, I'll get trans 2, and I get, let's take a look at this. We see that we get the same values here. Okay, so you can do it manually using mutate and dplyr, or you can just use the kind of built-in function for Box-Cox power transform, and it does it for you. So optional. So I think this is kind of easier. The only thing is that it says circulation raised to the negative 0.25 and add revenue to the negative 0.05, which is kind of cumbersome to type out. So what I like to then do afterwards is rename, change the names here by saying the names of trans 2 is going to be ty and tx. And this way, when I look at head of trans 2, it says ty tx, which I think is easier to deal with. Okay, so far so good. So this is using, so what we did, just to recap what we did is we fit the linear model. We said it was a bad fit. We took a look at the distribution of x, the distribution of y, and we said both of these are skewed, so we're going to transform both. Okay, and to transform both, the command we used, or to figure out what the appropriate transform to use, we used the command power transform. This creates estimates of what transform to use. We can use those estimates directly, or we might choose to use, quote, nice round numbers around those values, which I chose to do, which was negative 0.5 and negative 0.25. This is where people will probably, if different people did the analysis, they might differ here. Okay, this is one part where they might differ. Okay, so now that we have done this, we can try fitting the model here. Okay, so we can create a linear model between the transformed value of y and the transformed value of x. Okay, and we can also plot. So we can say take the numbers stored in trans 2, our second transform, and plot x and y, And let's just see what this looks like, okay? So keep in mind this was our, where did it go? This is our original data plot, right? So this, when we plot the data, it looks like this. After we transform it, this is what it looks like, okay? Or, you know, let me just get rid of the this smooth line. So this is without anything. So when we transform x and y, this looks pretty good, right? I'm like super impressed that the transform works this well, okay? It doesn't always work out this well. So this looks very clearly like a linear relationship with nice you know, constant variance and all of this stuff. And we can fit the linear model to this. We can create the model here, and we can look at the summary here. And we've got all this stuff here. Okay, we got a slope and an intercept. But now we just don't really know how to translate the slope and intercept. That's the only problem, okay? So after you transform variables, you know, an increase of 1 unit in x and the transformed x corresponds to an increase of 0.04 in the transformed y, but the transformed x is basically x raised to the negative quarter power, which I don't know what that has, what kind of literal interpretation that has, okay? So it just feels very odd trying to make interpretations directly off of this, okay? However, what we can do is we can create prediction intervals, and I think prediction intervals are very useful, okay? So I'm going to do part B here, which is create 95% prediction intervals for 500,000 and 20 million, okay? So here I've got x equal to 0.5 and x equal to 20, all right? And so I'm just going to say power transform 0.5 and 20 and do it to the negative 0.25 power, okay? So I can do this, all right? And then we get, oh, this is when you take 0.5 and you do the power transform, you get this number. If you take 20 and you do the power transform, you get this number, okay? So that's nice. For our prediction intervals to be useful, we want to undo the power transform, and there's unfortunately no built-in function for this. So I'm going to write a function to basically inverse the power transform. So just using algebra, I'm going to undo the power transform. So basically to get back to y, I'm going to just multiply the transformed value by lambda, add 1, and then take the lambda root, okay, or raise it to the 1 over lambda power, okay? So that's all I'm doing here, okay? So I'm just saying take the transformed value, multiply it by lambda, add 1, and raise it to the 1 over lambda power. That's all, okay? So I'm just creating a function, inverse power transform, to undo our thing, and we can see indeed if I take the XPRD and I apply the inverse power transform to it, I get back my original results of, or values of 0.5 and 20. Okay, so it's good that that works. Okay, so what I'm going to do is I'm going to create basically a bunch of prediction or the prediction values that I want to do. Okay, so I'm going to use the command predict to create prediction intervals. Okay, prediction intervals based on model 2, which is our transformed model right here. And I'm going to create predictions for the values, the powered x prediction values, okay, which we are these, right? We've transformed 0.5 and 20 million into the transformed values. And we're going to use that, and we're going to create our prediction interval, okay? So if I print this, yprd, this is what it fits, okay? So, you know, if I look at my my graph and I say, where does 2.1 end up on my graph here, and I go to 2.1, sure, it ends up around around right here, okay? And then if I go to negative 0.75, I end up right around here at 1.77. So at 2, I end up right around at 1.91. So, you know, this is just showing on the linear model where you end up, okay? So going at 2.1, I end up at 1.91, which is, you know, right around there, which matches what we see in the model, okay? But this is not useful to us, so we want to take the results here and apply our inverse function, okay? So basically it says, if you have a circulation of 500,000, we're going to predict 75,000, around 75,700 in ad revenue, with a lower and upper bound of 59 to 99,000. And over here, if you have a circulation of 20 million, we're going to predict you have ad revenue around, you know, 494,000, but anywhere from a lower bound of 279 to an upper bound of 1,095. Okay, so we got, this is our prediction interval. All right, are there any questions here so far? So the key here is we are using the power transform to get our x values into transformed x. We use our transformed x in our linear model to get predicted transformed y values. To turn our transformed y values back into real life y values, we have to undo the power transform. Okay, so it's a transform, predict, untransform. Is that okay? So that works. Okay, and then if we want, we can plot our prediction interval, and this is a little bit more involved. Okay, I'm creating here. Here, I'll let you see the entire code. I'm creating the entire. I'm looking at the range of circulation. So range of circulation will give me, just so you can see, the smallest value in range to the largest value in range. Okay, so the smallest one is like that Bridal magazine with 3.331 million, and then the large is Parade with 32 million. Parade is like, I think they stuff it in like the Sunday magazine or Sunday newspaper. Do you know what I'm talking about? It's like that junky magazine that they kind of just stuff in Sunday papers. So I don't think anybody actually subscribes to it. Like they're like, oh my God, Parade, yay. But I think it just shows up in their Sunday papers. So I think that's why the circulation numbers are so high. Okay. So anyway, we do this, and we're just going to create just a large sequence. So if we look at xpredict, it's just a sequence of numbers from the smallest to the largest, right? Because we're only supposed to make predictions for the area where we've collected data. We're not supposed to predict outside of that. This is one of the regression 101 rules, right? This is actually regression 101, right? Okay, so we're going to then apply the power transform. So I'm going to call this xpredict transform. We're going to apply the power transform to all of these. Okay, and based on these transformed values, now I'm creating my prediction interval. Okay, so I'm using the same command that I used before, and I'm creating my prediction intervals. Is this step by step okay? So it's just like what I did over here, but now instead of giving it 2 values, I'm giving it 100 values. Okay, and then now to plot these back on our graph, I'm going to undo the power transform for y and undo the power transform for x, and I'm binding them together just in a matrix or in a data frame called yPRD for y predictions. Okay, so now I'm going to plot these. Okay, so this is just plotting the prediction line. Okay, and here now I'm going to add the prediction interval. Okay, so we can see the prediction interval has a lot of spread here, and then we're going to add the points. Okay, And so here's our prediction interval for our data here. And I'd say this looks pretty good, right? Okay, so our prediction interval for all of our data, so we see it kind of spreads, and this is what we get. Okay, and so this one, you know, has a pretty sizable outlier compared to our prediction line, but this is what we have. Okay, is that all right? I guess you know, one thing I forgot to do is back when we created our transformed model, I should have looked at the diagnostic plots for model 2. So if we look at the diagnostic plots, this is the residual plot. That looks pretty good. It looks like it's pretty random. This is our QQ normal. This looks pretty good also. This is our scale location plot. Also, these all have nice properties here. Okay, and this is our residual versus leverage. Also, I'd say this looks pretty good. Okay, we don't have anything with very high Cook's distance once we get a linear plot here. Okay, so that is, you know, transforming x and transforming y and fitting a linear model. Okay, so the other part, so I'll let you guys do that, and then you can describe the weaknesses and things like that as part of your homework. And then part B says develop a polynomial regression model. And so I know we haven't covered polynomial regression, but basically it's just like linear regression, except you're throwing in some polynomial terms. So linear regression was y is equal to beta 0 plus beta 1x plus error. Polynomial regression is y is equal to beta 0 plus beta 1x plus beta 2x squared plus beta 3x cubed, whatever, etc., plus error. So you're still assuming constant variance here, okay? So let's try this out, okay? We're going to do polynomial regression. And so the way you create polynomial regression in R is you do linear model between ad revenue and circulation, and then for x squared you do I circulation squared, and then for the x cubed you have to do I circulation cubed. Okay, and then data ad revenue as always. So this is how you fit a polynomial model here. Okay, so we're going to do that. We can ask for the summary of the polynomial model, and it says all of your terms, the intercept circulation, the squared term, and the cubed term, they're all significant. Okay, and okay, and so we're going to fit the line here. Okay, and so plotting this is kind of a headache. All right, so I've got to create kind of our, using the same tactics that we did for the prediction interval here, we're going to plot the prediction interval for the polynomial regression. Okay, so first I'm creating just a range of circulation values. Okay, so just from the smallest circulation to the largest circulation, I'm just creating a range of 100 values, so I can look at you know, PRD, and again starting at the smallest circulation to the largest, we do that. Okay, and then we're going to fit create a prediction interval, and I'm going to create a data frame there. Okay, and so we can see these are all the fitted values for our prediction interval here. Okay, and so because these are not transformed, I can just go straight. I don't have to worry about transforming and untransforming. So here, and then I'm going to just bind the x values to the prediction values. So I'm going to column bind the prediction values and the predicted values here. Okay, have I lost anybody yet? Are we all okay? We're okay. Okay, so here is our prediction thing. So everything is kind of, this is in millions and this is in thousands, right? This is in the units we're expecting. Okay, so we're going to plot this. All right, so again, keep in mind our original data plot looks like this, and we're going to try to fit a polynomial regression. So using our prediction values, we're going to plot x and y, and then add the smooth line and our dots. So we go ahead and do this, and this is what we get. Okay. So essentially, again, we're kind of assuming constant variance, so you see kind of the same width for the entire prediction interval as we go along. And how do you guys feel about this? All right, so, okay, and then, you know, we can plot the standardized residuals. Okay, and this is what our standardized residual plot looks like, and I don't know if we have an opinion on that. And we can also do the diagnostic plots here. Okay, so plotting them one by one. So this is just the residuals versus fitted. You know, I don't know if you feel like there's a pattern, yes or no. This is our normal QQ plot. Okay, so it seems like, yeah, there might be some problems here. Okay, that you might want to talk about. Our scale location plot, what do you think here? Good or bad? I think there's some problems, right? This is definitely showing signs of increase here, so it seems like we don't have constant variance in our model, so it seems like there's definitely some issues, and we're getting some errors here, but we notice we're going to have some very large Cook's distance values here also. Okay, so and looking at the at this plot, okay, I get the sense that we are overfitting our data. Okay, we only have one data point out here. And so with polynomial regression, it's easy to fit that one data point exactly. But, you know, if there were to be another magazine with 32 million subscribers, do you think it's going to have this kind of this exact same range out here? Yeah, probably not. And it's probably not a very good idea to assume that we have the same amount of variance for ad revenue when it comes to a magazine with 32 million subscribers as we would for a magazine with, you know, under 1 million subscribers. Okay, we're probably not going to see the same amount of variance. I think it makes a lot more sense that when we're talking about the variance in ad revenue, the variance in ad revenue for small magazines will probably be much smaller, and for very big magazines will probably be much bigger. I think that makes sense. And so this regression model, although, you know, it has these nice properties of kind of fitting our model well, I feel like there's some serious deficiencies with it. Okay, so be sure to talk about that in your homework. Okay, are there questions here on this homework exercise? Okay, I hope this is helpful in doing your homework. Okay, so yeah, I'm sorry, I hesitate to post this code directly online because I'm just afraid you're going to copy and paste it into your homework, which I feel defeats the point. You know, even if you just pause the video here and then you type it in by hand, I feel like that's much better than copying and pasting. Okay, so even if you just type this exactly as it appears, as long as you're typing it by hand, I think there's some brain activity saying, oh, this is the command I have to type. I feel much better about that. So I'll pause right here on this screen for a few seconds, and you can pause here, and then I'm going to scroll back up, and we'll start at the beginning, okay? And if you want to pause the video here Okay, you can do that. All right, and then I'm going to scroll down, and if you want to pause the video right here, also fine. And we'll scroll down to here also. Okay, and I think that covers all of the code. I feel much better about you, even if you want to copy my code directly, as if you're typing it by hand, I feel better about that. Okay. All right. Issues, questions on that? Okay. Well, let's look at the first problem, and we're probably going to just run out of time before we get to the fifth one. Okay, so here it says airfares.txt, and it says it fit a linear model, and it says something like this. Okay, you know, when you plot it, hey, that looks pretty good, right? A linear model, and it says you know, your r squared value is 0.994, which is very high, and so it says something like distance is highly statistically significant, and the model explains 99.4% of the variability in the y variable, the fare. Thus, model 1 is highly effective model for both understanding the effects of distance on fare and for predicting future values of fare given the value of the predictor variable distance. Okay, how do we feel about this? Okay, this is our standardized residual plot. What do we think? So we're probably, there's going to be some, again, because statistics is dealing with real life data, the answers aren't always clean cut, okay? Here it seems like there's definitely some kind of pattern, right, in our standardized residual plot, okay? We got some kind of thing. And then we also have this one outlier here with the standardized residual of +3, which is pretty high. I mean, it's certainly possible, but it seems pretty high. And that seems to throw things off. And so when we look at this statement, yes, we have an r squared of 99.4%, or explaining that the model explains 99.4% of the variability in y. And that is, you know, for the linear model, that's true. But, you know, this statement, highly effective for both understanding the effects of distance on fare and for predicting future values of fare. I would say it's probably good for predicting future values of fare. But understanding the distance on, understanding the effect of distance on fare is probably not accurate, okay? Whenever you have, so the true model might have some kind of shape like this, okay, that, you know, we're not really picking up because the linear part is kind of overwhelming everything. Can you make good predictions? You can probably make pretty good predictions. There's probably going to be something that's deficient in your model. But there's an old saying that says all models are wrong, but some are useful. And I would say this would be a case where you have the wrong model, because clearly this shows something is wrong with your model. But because the dots follow the lines super well, it's probably going to be useful in making predictions, okay? So this would be a case where you have the wrong model, but it's still fairly useful. And it's kind of like all of these kind of rules of thumb where we know that's not actually the case. Like, you've probably heard, have you heard of the rule of 72 for like interest and doubling your account? And it's like, you just take, if you earn 4% interest per year, you do 72 divided by 4, and you get 18, and that's supposed to be how many years it takes to double your money. That's not super accurate, but it's useful, okay? And so this is a case where the model is wrong, but it's probably useful. I've tried a few things, and you don't have to do it this way. Here I'm showing my solutions. So what I have done is, you know, I went ahead and I fit all of this this stuff, and you know, we just try fitting the linear model. And when we fit the linear model, whoops. So this is the standardized residual plot. And we see, okay, yeah, we get that curved pattern, which indicates something is wrong, okay? So, you know, we might consider, I can plot the Cook's distance, okay? And if here's a Cook's distance plot for the data that we have, and we see the two flights with the largest distance have very high Cook's distance, okay? And so these are very influential in our in determining our regression model, according to this. So unfortunately, we don't have very much information about these two flights with great distance. So it's hard to say, you know, whether we should remove them or not, okay? If we look at the QQ plot, again, the two flights with the greatest distance actually show up 13 and 17, 13, 16, and 17. But it's really 13 and 17. These are the ones with the kind of the craziest residuals, and they show up. So, you know, I'm going to try transforming the y variable using an inverse response plot, okay? And using the inverse response plot, it says the best transformation is 1.02. Basically, it means leave your data untransformed, okay? Which is probably, I think, influenced by the fact that I have these two outliers that kind of are pulling our linear line out that way, where maybe there's actually kind of more of a slight curvature out here. And so I'm going to try removing those two flights, okay? So I'm going to create a new x and a new y just by removing those two flights. And so again, it's not a good idea just to remove data just for the sake of removing data. But here their Cook's distance was high. I don't know anything more about these flights. So what I'm going to say in my analysis is that these seemed like outliers because of their incredibly high Cook's distance. I'm going to remove them from the analysis and see what happens. However, what this means is that any conclusions I make from my new model cannot be extended beyond the flights where I have data now, okay? So basically, now that I'm removing these two flights, the range where my model is useful is now up to this point, okay? Beyond this point, my model is no longer useful. So we have to keep in mind, whenever you're removing data or things like that, you lose the usefulness of your model. So I'm going to fit a new linear model, okay? And here, and actually let's do let's take out our two things and just see what our plot looks like without them. Something happened here. Okay, something went wrong. Okay, well here, so I'm just, this is just a standardized residual plot of the new model without the two extreme outliers. We're seeing some kind of pattern here. So I'm going to fit the inverse response plot, and it says, and now it says the best transformation is 1.27. So I'm going to try doing that, okay, and we're going to try fitting our data, and we're going to see what happens there. And when we transform our data, we see our standardized residual plot looks a little bit better. But, you know, was that the right thing to do? It's hard to say. It's hard to say. A lot of this stuff with regression is you're trying to do your best, and it's hard to know without more information. If you only have the data, it's hard to know whether you should take certain points out. Okay, we have indicators like the Cook's distance that says maybe these points are a little strange. Okay, so who knows? Maybe. So what it could be is that there's might be some kind of relationship where as distance increases, fair goes up, but maybe the true relationship is that it kind of levels off. However, maybe there's something special because they were super long distance. Maybe they have to do something, and there's another term that increases the cost of the flight. So maybe maybe this increases because of the cost of fuel. As distance goes up, the cost of fuel, the fare goes up because of the cost of fuel. But maybe also at a certain point, when it gets really far, then you need, I don't know, a second crew or something. You got to pay the airline attendants overtime or something. I don't know. Maybe there's something funny going on that kind of sticks it back. Okay, so maybe the true trend goes like this until you get out here where, I don't know, something strange happens. We don't know. We don't know what it is about these two flights. We can remove them and try the analysis without them. We can leave them in. Okay, anyway, I hope today's lecture is helpful, at least in getting you through this week's homework. I have office hours tomorrow, so if you're still stuck, still confused, don't hesitate to pay me a visit. Okay, we'll see you guys.